Welcome to the class. As we were started discussing, we will again discuss about some more worked out examples. Today we will discuss about the engine cycles. So an example of turbojet engine is read as: a turbojet engine is operating at Mach number 0.6 with following conditions, and calculate specific fuel consumption for this engine. Compressor efficiency is given as 85%. Intake efficiency is 93%, turbine efficiency is 95%, nozzle efficiency is 95%. Overall, our compressor pressure ratio is 6. Combustion chamber pressure loss is 5% of delivery pressure. Fuel air ratio and combustion efficiency is 0.0137 and 0.98 respectively. Turbine inlet and stagnation condition is 1000 Kelvin. Mechanical efficiency is 99%. Assume ambient pressure as 0.265 bar and temperature 223 Kelvin. Consider Cp of air as 1.005 and ratio as 1.4. Cp of gas is 1.147 and its specific heat ratio as 1.33. Here we are supposed to calculate specific fuel consumption. So let us note down first all the given things. So given as read in the example, Mach number is given as 0.6, atmospheric pressure is given as 0.265 bar, then ambient temperature is given as 223.3 Kelvin, turbine inlet temperature for us T03, which is T max, is given as 1000 Kelvin. Then overall pressure ratio or compressor pressure ratio is 6, and then it is told that compressor efficiency is 85%, turbine efficiency is 95%, intake efficiency is 95%, 93%, nozzle efficiency is 95%, combustion efficiency or burner efficiency is 0.98, mechanical efficiency is 0.99, then Cp of air 1.005, Cp of gas 1.147 kilojoule per kg Kelvin, kilojoule per kg Kelvin, gamma of air 1.4, gamma of gas 1.33. Further, fuel air ratio is given as 0.0137. Now we have to solve for specific fuel consumption. First, let us draw a sketch for the order of the components which air will encounter. This is intake. Atmospheric condition will go into the intake, and then we will number as 01. At 01 it will go into the compressor, it will come out as 02, then it will go to combustion chamber, then it will come out to 03, then it will go to turbine, and then it is 04, then it will go to nozzle, and it is 5. Exit is static condition, it is 5, but turbine is connected to the compressor, so that there is net work out to be 0. So let us first start for solving from intake. We know for specific fuel consumption we need to calculate thrust. So first for thrust calculation we should know everything at the nozzle, that is nozzle exit velocity Cj, and then that is why we have to start from intake. So in the intake we are told that atmospheric temperature is told, so we can know T0 A upon Ta is 1 plus gamma minus 1 by 2 m square. So Mach number is 0.6, so this will turn out to be 1.72. So this gives us T01 is equal to TA into 1.072. This gives us T01 as 239.37 Kelvin. We can find out Cj minus Ca, that is aircraft speed, which is Ca, that is Mach number into acoustic speed. Mach number is 0.6, acoustic speed is under root gamma r Ta. So it is 0.6 into square root of 1.4 into 287 into 223.3, and this gives us velocity as 179.72 meters per second. Then we know now what is the velocity at the ambience condition. Now let us find out what is the pressure at the outlet of the intake. So we know this is the pressure ratio across which intake is working, but it is non-ideal intake. It has certain efficiency. So using that efficiency we can calculate the pressure rise or total pressure at the outlet of the intake, that is P01 upon Pa is equal to 1 plus intake efficiency, which is 0.93 into Ca square divided by twice Cp Ta, that is for air. So it is 1 plus 0.93 into Ca square 179.72 square divided by 2 into 1005 into Ta 223.3, gamma A upon gamma minus 1 for air is 3.5, and this gives us 1.0669 bracket raised to 3.5, and hence it is 1.2544. So we can calculate P01 is equal to Pa into 1.2544. So P01 is equal to 0.332 bar. This is the intake calculation. We can go ahead and do calculation for compressor. We know intake is a non-work addition device, so there is no change in total temperature. So total temperature is same, which is 239.37. P02 is Rp for compressor into P01. So it is 6 into 0.332. So it is 1.9946 bar. So this is the total pressure at the outlet of the compressor. Knowing this, we can find out temperature at the outlet of the compressor. We know it has no 100% efficiency, so with the efficiency we can calculate actual change in temperature in the compressor is equal to T01 divided by efficiency into P02 divided by P01 bracket raised to gamma A minus 1 upon gamma A minus 1. We know how to derive this formula. It is actually compressor efficiency is equal to ideal work input divided by actual work input. So actual temperature difference is equal to 1 upon compressor efficiency into ideal temperature difference. We can take T01 common from right hand side. So we will have T01 into efficiency divided by efficiency into T02 dash divided by T01 minus 1. we know that T naught 2 dash upon T naught 1 is P naught 2 divided by P naught 1 bracket raised to gamma A minus 1 upon gamma A. This is what the derivation for this formula is. So we know now T naught 2 minus T naught 1 is equal to 239.37 divided by 85% compressor efficiency, so into 6 bracket raised to 0.286 minus 1. So this gives us actual temperature difference as 188.5 Kelvin. So we can find out total temperature at the exit of the compressor as 427.87 Kelvin. Now we know everything at the compressor output or outlet. We can work out for the combustion chamber. We know the exit temperature for the combustion chamber is 1000 Kelvin, but we don't know what is pressure, but we are told that it is loss is 5% for the delivery pressure. So 5% will get lost, so 0.052 into P naught. So P naught 3 is equal to 0.95 into P naught 2, and P naught 2 is known to us. It is from there can be calculated as 1.8948 bar. Since P naught 2 is 1.9946 bar. Now we know everything at the combustion chamber outlet. We can go ahead for the turbine. For the turbine, we now can make use of the fact that turbine work actually has to be equal to compressor work for 100% mechanical efficiency. If it is not 100%, then turbine has to do more work. So turbine work is equal to compressor work divided by mechanical efficiency. We know turbine work is equal to Cp of gas into T naught 3 minus T naught 4. We know compressor work is Cp of air into T naught 2 minus T naught 1 divided by mechanical efficiency. So we can find out temperature change in the turbine as Cp of air into T naught 2 minus T naught 1 divided by Cp of gas into mechanical efficiency. So total temperature change in the turbine is equal to 1.005 T naught 2 minus T naught 1. We know it is 188.5 divided by Cp of gas 1.147 into efficiency, mechanical efficiency, which is 0.99. So T naught 3 minus T naught 4 is equal to 166.68 Kelvin. From here we can find out T naught 4 is equal to T naught 3 minus 166.68 Kelvin, which gives us it as 833.31 Kelvin. This is the temperature at the outlet of the turbine. We need to find out pressure as well. For that, first we will find out temperature which is ideal at the outlet of the turbine. For that, we can make use of turbine efficiency and that turbine efficiency is actual turbine work output divided by ideal turbine work output. So it is T03 minus T04 dash is equal to 1 upon turbine efficiency into actual T03 minus T04. So ideal temperature at the outlet of the turbine is equal to T03 minus turbine efficiency into T03 minus T04. We know T03 is equal to 1000 minus turbine efficiency is known to us, and that is 0.95, and then we just have found out the temperature difference, which is real 166.68. So T04 dash is equal to 824.54 Kelvin. Knowing this, we can find out what is the pressure ratio which turbine was operating upon, which is P04 divided by P03 is equal, that is 1 upon Rp turbine bracket raised to gamma minus 1 upon gamma, and this is for gas, which is equal to T04 dash upon T03, and that is bracket raised to gamma gas divided by gamma gas minus 1. So we know it is 824.54 divided by 1000 bracket raised to 1.33 divided by 0.3, and this ratio turns out to be 0.4583. From here we can find out the total pressure at the entry to the nozzle, which is P04 is equal to P03 into 0.4583. So it is 0.8684 bar. So this is what the calculation till the entry to the nozzle. We can go ahead and calculate the things for nozzle. So here nozzle governing pressure ratio is equal to P04 divided by P ambient, which is 0.8684 divided by 0.265, which is ambient pressure, and this ratio turns out to be 3.2769. We don't know what is the state of the nozzle, that means whether the nozzle is choked or not. For that we have to find out the choking condition of the nozzle, which is P04 by Pc from the nozzle efficiency, which is 1 minus 1 upon Nj. Nj is nozzle efficiency, gamma g minus 1 divided by gamma g plus 1 bracket raised to minus gamma g upon gamma g minus 1, and then we know that gamma g is 1.33. we can put it over here. We are told that nozzle efficiency is 95, so it is 0.95. so putting all these numbers, we get this ratio as 1.91. we can compare these two ratios and then find out whether it is choked, but before that we can also do calculation for Pc. It is 0.8684 divided by 1.91, so it is 0.4546 bar. We know atmospheric pressure is 0.265 bar. So the choking pressure is higher than atmospheric pressure, so there is enough scope for expansion, so nozzle is choked, So we can say that nozzle is choked. And then we know for the tall sake jet pressure is 0.4546 bar. We need to find out that time AJ, which is equal to CJ, which is equal to A5, which is gamma R T5, and this is for gas. And for all sake we will take this R for air, which is similar. For this we need T5, so T5 is basically is equal to Tc is equal to 2 upon gamma G plus 1 into T04, and it turns out to be 715.28 Kelvin. So now we can calculate Cj as square root of 131.33 into 287 into 715.28. So the jet velocity at the exit is 522.52 meters per second. For unit mass flow rate we can find out area, which is equal to mj divided by rho j into Cj, but we are considering unit mass flow rate, so rho j is Pj upon Rtj into Cj, so it is R into Tj divided by Pj into Cj. So the jet area for unit mass flow rate is 0.0087 meter square. Assume m dot is equal to 1 kg per second. So for unit mass flow rate, thrust can be calculated as Cj minus Ca plus A divided by mj, which is rather area per unit mass flow rate, into Pj minus Pa. So we know now Cj, we have found out Cj, we know now Ca, which is the aircraft speed, so Cj minus Ca turns out to be 342.18 plus area, which is found out 0.0087, Pj is 0.4546 bar, Pa is 0.265 bar. So from there it is 160.95, and this turns out to be force as 503.43. So we can find out specific fuel consumption, and that is fuel air ratio divided by force. Okay, but here this is at this moment we are said that this turbojet has combustion efficiency, so we can say fuel air ratio theoretical divided by burner or combustion efficiency divided by jet thrust. This will be in seconds, so we will make it into hours by multiplying 3600. So SFC is equal to 0.137, which is given as fuel air ratio, that is fuel flow rate for unit mass flow rate of air. In the bottom we have force per unit specific force, specific thrust, thrust per unit mass flow rate divided by combustion efficiency into Fj into 3600, and this value turns out to be 0.099 kg per hour Newton. So this is the example what we are trying to solve. We will move ahead to the next example, and then this example is for the turbofan engine. It says that the following data applies to a twin spool turbofan engine with the fan driven by LP turbine and compressor by the HP turbine. Separate cold and hot nozzles are used. Overall pressure ratio is 23, fan pressure ratio is 1.65, isentropic efficiency of each nozzle is 0.95, bypass ratio is 5, turbine inlet temperature is 1500, compressor and turbine polytropic efficiency are 0.9, mechanical efficiency of spool is 0.99, air mass flow is 190 and combustion pressure loss is 1.5 bar, burner efficiency is 0.99, fuel air ratio is 0.0205. It is required to find specific fuel consumption for static condition. Atmospheric pressure and temperature as given as 1 bar and 298 Kelvin, and as it is expected, it is given that the air and gas has different specific heats and different gas specific heat ratios. As given in the example, we can mention few things. Before that, we can sketch now, since there are too many spools, so we can sketch here. We have fan, then from before the fan we have atmospheric condition, which is basically not 1 since it is also stagnant. Then there is compressor. From the fan there is also one more thing, which is nozzle, and then there is exit. From the compressor, air goes to the combustion chamber. From combustion chamber it goes to the high pressure turbine. After high pressure turbine it goes to low pressure turbine and then hot nozzle. So here we will say it as not 2. As it is said in the example, high pressure turbine is connected to the compressor and low pressure turbine is connected to the fan. So their works are same. So this is also not 2 but reduced mass. Here you have m dot c, here you have m dot h. And then we have not 3 at the combustion inlet, not 4 at the high pressure turbine, not 5 at the low pressure turbine inlet, not 6 at the nozzle inlet, and 7 at hot nozzle outlet, and 8 as cold nozzle outlet. We will say it as hot and we will say it as cold. And this is representation of turbo fan engine. Knowing this, we can write down few things which are given. We are given with pressure ratio which is overall, and that is 23. Fan pressure ratio is 1.65. We are told compressor combustion maximum temperature in the cycle, which is at the exit of the combustion chamber, so it is T04, it is 1500 Kelvin. Mechanical efficiency of both the spools is 99. Bypass ratio is 5. P01 to ambient condition 1 bar. T01 ambient condition 298 Kelvin. Compressors propulsive efficiency, turbines propulsive efficiency, and then they are given as 0.9. Efficiency of both the nozzles, hot or cold, is given as 95%. Okay, and then we have burner efficiency as well, and it is given as 0.99. Delta P naught combustion chamber is told as 1.5 bar. Fuel air ratio over here is 0.0205. M dot is 190 kg per second, and rest gamma G 1.33, gamma A 1.4, CPG 1.148 and CPA 1.005 kilojoule per kg Kelvin. This is also kilojoule per kg Kelvin. Noting this, we can start solving the example. Again, here as well we have to find out specific fuel consumption. So for that we need to find out thrust. Thrust needed to be found out from cold nozzle and hot nozzle. We have to add that and then find out the specific fuel consumption. So we know fan pressure ratio P02 upon P01 is 1.65. So we have P02 is 1.65 bar, since P01 is 1 bar. Now after the fan there is cold nozzle. So the gas which is at P02 is going to enter to the cold nozzle. So we have to see if this nozzle is choked. For that again we have to see for choking condition, P02 upon Pc is equal to 1 minus nozzle efficiency. Since this nozzle has air, so we can use gamma for air, which is gamma air minus 1 divided by gamma air plus 1, bracket raised to minus gamma air divided by gamma air minus 1. So we can write down it as 1 minus 0.95 into 1.4 minus 1 divided by 1.4 plus 1, bracket raised to minus 3.5. This gives us this ratio as 1.96. So Pc turns out to be P02 divided by 1.96 and Pc is 0.8399 bar. If we see choking pressure, it is lower than atmosphere. So we can say that nozzle is not choked. So gas will attain atmospheric pressure at the exit. So for that we have to find out the velocity at the exit. So that is due to enthalpy change. We can find out T02 minus T8, which is the total temperature at the inlet minus static temperature at the outlet of the cold nozzle. This gives us Nj into T02 into 1 minus 1 upon P02 divided by Pa, bracket raised to gamma A minus 1 upon gamma A. So this is 0.95 into T02 and T02 is 349.33 into 0.1334. So T02 minus T8 is equal to, into the bracket, 1 minus 1 upon 1.65 bracket raised to 0.286, and then this turns out to be 44.27 Kelvin. So exit velocity of the jet is 2 into Cp of air into delta T naught. So and square root of this. So it is 298.3 meters per second. This is the velocity, but we know that bypass ratio is 5. So mass flow rate through the fan is total mass flow rate into bypass ratio divided by bypass ratio plus 1. So 190 into 5 plus divided by 6, and it is 158.33 kg per second. So we can say cold thrust is equal to m dot c into C8 minus Ca, but Ca is 0, so it is C8 alone, and that turns out to be 47.23 kilonewton. High pressure turbine calculations we will start. And for high pressure turbine, it is taking hot air and then it is doing the work, which is T03 minus T02 into Cpa. This work is given to the compressor. So this is the compressor work input divided by mechanical efficiency, and that is equal to the high pressure turbines work. So Cp of gas into T04 minus T05 into hot gas, which is coming into the compressor to the turbine. So MH, both the mass flow rates are same for the compressor and turbine, so it gets cancelled. We can find out T04 minus T05 is equal to Cp air into T03 minus T02 divided by mechanical efficiency into Cp of gas. Here we are not knowing what is the temperature at the entry to the combustion chamber or at the exit of the compressor. So that can be found out from given polytropic efficiency of the compressor. So we will name it as equation 1, since we do not know what is T03. It can be found out from polytropic efficiency, which says that n minus 1 upon n is equal to polytropic efficiency of compressor into gamma of air minus 1 upon gamma of air. So it is 0.9 into 0.4 divided by 1.4, and it is 0.3174. So further we are told that Rp overall is given as 23, so it is Rp fan into Rp compressor. So Rp compressor is equal to Rp overall divided by Rp fan, so it is 23 divided by 1.65, and it turns out to be 13.93. So this is the pressure ratio for compressors. Now we can say T03 upon T02 is equal to P03 upon P02 bracket raised to n minus 1 upon n, and P03 minus P03 divided by P02 is known to us, which is 13.93 bracket raised to 0.3174. So T03 is equal to T02 into 13.93 bracket raised to 0.3174. This gives us T03, which is 805.98 Kelvin. Now we can go to equation 1, and there we can put everything and find out T04 minus T05 is equal to 1.005 into T03. We have just found out 805.98, and T02 we know it 349.33 divided by mechanical efficiency 0.99 into 1.148. So knowing this, T04 minus T05 is equal to 403.8 Kelvin. So we can find out T05 is equal to T04 minus 403.8 we know T04, which is given temperature as 1500 Kelvin. From there we get T05 as 1096.2 Kelvin. Now similarly we can go to the low pressure turbine, and here we can say that low pressure turbine will have its work equal to fan work, and fan work is fan is interacting with complete air, so it is m dot into Cp air into T02 minus T01 divided by mechanical efficiency. But LP turbine interacts with only hot mass, so Cp of hot gas into mass flow rate of hot gas into T05 minus T06. So T05 minus T06 is equal to m dot and divided by m dot h, but m dot h can be written as m dot minus m dot c into Cp of air divided by Cp of gas into 1 upon mechanical efficiency into T02 minus T01. So T05 minus T06 is 190 divided by 190 minus 158.33 into Cp of air 1.005, Cp of gas 1.148, mechanical efficiency 0.99, and T02 349.33 minus 298. Having said this, we can find out T05 minus T06 as 272.311 Kelvin. So this is the temperature drop into the low pressure turbine. Now we can move ahead and work out for hot nozzle. For hot nozzle, now we know conditions at the inlet, and those conditions are the pressure and temperature at the inlet. So we can then find out what is the choking condition for this nozzle first. So P06 divided by Pc will be 1 minus nozzle efficiency into gamma gas minus 1 divided by gamma gas plus 1. So this is equal to 1 upon 0.95 into bracket raised to minus gamma gas divided by gamma gas plus 1. Minus gamma gas upon gamma gas plus 1 minus 1. Knowing this, we can find out P06 upon Pc as 1.9168. So from here we can find out Pc, which is P06 divided by 1.9168. But here we don't know P06, so we will name this equation as equation number 2. Here we know P01 is 1 bar, then we know P02 is 1.65 bar, then we know there is combustion chamber, there is P03 which is P02 which is risen to P03 in the compressor. So P03 was 22.98 bar, which is based upon the pressure ratio of the compressor. Then there is loss in the total pressure, which is 1.5 bar, so it is 21.48 bar. So now we know polytropic efficiency of turbine. So polytropic efficiency of turbine 1n minus 1 upon n is eta T into gamma g minus 1 upon gamma g, so which is equal to, so this is polytropic efficiency of turbine 0.9 into 0.33 divided by 1.33, and this gives us 0.2248. Knowing this, we can find out P04 divided by P05, that P04 and 5 is for high pressure turbine. High pressure turbine pressure ratio is equal to T04 divided by T05 bracket raised to n upon n minus 1. We know T04 is 1500, T05 1096.2 bracket raised to 1 upon 0.2248, and then this pressure ratio turns out to be 4.035. From here we can find out P05, which is 21.48 divided by 4.35, and that turns out to be 5.322 bar. Similarly, P05 divided by P06 is equal to T05 divided by T06 bracket raised to n minus 1 upon n. T05 is 1096.2 and T06 is 823. We can find out from here which is T06, and this gives us T06 to be 823.88 Kelvin. Since we know P05 now, which we can make use of here, 823.88 bracket raised to 1 upon 0.2248, and this gives us the ratio as 3.56 to 1. From here we can find out P06, and P06 is 1.494 bar. So comparing from here we can know that PC is equal to P06 upon 1.9168. It turns out to be, it is less than PA, since PA is 1 bar. So we will have nozzle not choked. So we can go ahead and then find out what is the temperature drop across the nozzle. Hot nozzle T06 minus T7, which is Nj into T06 into 1 minus 1 upon P06 divided by PA bracket raised to gamma g minus 1 upon gamma g, and then this turns out to be, putting all the numbers, this will turn out to be 78.61 Kelvin. We can find out Cj is equal to C7 is equal to square root of 2 into Cp of gas into T06 minus T7. We can put T06 minus T7, we know Cp, and then we can find out it to be 424.83 meters per second. So we can find out hot thrust is equal to m dot h into C7. So it is m dot minus m dot c into C7. So we have hot thrust is equal to 190 minus 158.33 into C7. C7 is 424.83. So this gives us hot thrust as 13.454 kilonewton. So we have total thrust from the jet is equal to cold thrust plus hot thrust. So cold thrust we know it is 47.23, hot thrust is for 13.45 and gives us total thrust as 60.68 kilonewton. We are told that fuel air ratio is 0.0205, but we know m dot is equal to m dot fuel. We can find out, which is m dot h mass flow rate of air into fuel divided by burner efficiency, and it turns out to be 0.655 kg per second. So specific fuel consumption is m dot f divided by fj, and this turns out to be 0.0388 kg per hour Newton, where it is expected that we have taken m dot f in kg per second, thrust in Newton, and then we have multiplied by 3600 to get second converted into hour. So these are the some practiced examples, some more for our and better understanding.